So we had said that with these Z procedures, this is all based off of the normal distribution. And these three conditions right here are theoretical qualifications that we need. Okay? We need random data. Okay? That's good. I mean, we know that that's always something that's important for us. The population is normal. Well, that isn't as important. Okay? Theoretically, yes, we want that, but we had seen with the central limit theorem that that's based off of the sampling distribution. These Z procedures are based off of theoretically taking a bunch of samples, and we know that as long as the sample size is large enough, and that's kind of intentionally a vague term, but as long as that sample size is large enough, that the distribution of the samples will be normal. So that's okay. Lastly, I've already said how this is kind of a ridiculous assumption that we would know the population standard deviation, when the whole point of this is to learn the population's mean, and you can't get this parameter without knowing the mean. So usually the sample standard deviation is going to be sufficient for us. We'll more formally show how we can avoid using that parameter right there in our next test that we'll be learning in a few weeks. Now, the big thing from Thursday is that the data that we collect is still important. Everything that we talked about with our sampling design, our experimental design in the first semester, that's what's really important, is that we make sure that we have good, accurate, and authentic data that's representative of the population that it's describing, that sample size is large enough. We can't expect to get good results if that data is not good. I talked about how two of the biggest problems that we've seen are non-response and undercoverage. Those are the two things that are still impacting, like we see it at the last two presidential elections. That the polling results leading up to the general election, they're not really predicting what's actually happening, okay? Not within the margin of error because of undercoverage. They're having trouble reaching certain pockets of the population and non-response. When they do reach people, the people are reluctant to participate. And those who do want to participate oftentimes have strong opinions, strong views, and it's almost turning into a voluntary response sample, which we know is not good. They tend to be more biased. So what happens is, it's not surprising in that respect when you're weighing all of these considerations that you get a confidence interval that's saying we expect the actual value to be between here and here, but you're getting results, real results that misfire. And they're down here, they're down here. Okay? When you have that systematically occurring, there has to be a reason for it, and it's these two reasons. It's not an easy fix. But for us, they are still problems because sometimes we get this misconception that we're protected by the margin of error. That the confidence interval allows us some leeway that we don't need to be precise, or we can kind of cut some corners or take some shortcuts in our data collection because the margin of error or the confidence interval allows us to be between here and here. We don't have to be right there. But the confidence interval is specifically made for the natural variation. And you flip a coin 10 times, you expect 5 heads, 5 tails. If you get 6 and 4, or maybe 7 and 3, that happens from time to time, and the confidence interval allows for that. It does not allow for poor data collection or biased data collection. Sometimes that's what people are mistaken about. So we went through here. This slide right here is kind of the basis for what we'll be talking about with our error analysis. Okay? How small of a p-value is convincing? we know that a lot of times we're comparing it to this 0.05 level of significance. So anything less than 0.05, we reject the null, accept the alternative hypothesis. There's the answer to the yes or no question of, is this a significant difference or not? In its most basic and blunt form, that's what a hypothesis test does. It gives you a yes or no question about the statistical significance. However, you can read more into it and get more out of it by looking at this p-value. I had said that if you had set a p-value of, or an alpha level of 0.05, and you come back and your test gives you 0.047, you as the researcher might be thrilled because the last 2 years or however long your research has taken you yielded a statistically significant result. Okay? That's good, but just barely. It's just barely below the threshold that you set. Okay? Are your interpretations any different if you had come back with a p-value of 0.000001? They should be, because this is a very convincing p-value that would be good at a much smaller alpha level. Remember, p is a probability. It's the probability that you would expect the null hypothesis to be true, that you would expect this value, and your data would give you this value, your evidence, and that difference is just due to chance variation alone. You want a small p-value because that's saying, no, this probability is so low and so rare that it's natural variation alone that you expect this and you got this just as a fluke and it happens. No, this is saying that that's incredibly rare, that it's probably not natural variation, and that there is meaningful evidence here that this is truly what's happening. So we should reject that null hypothesis and accept the alternative. As opposed to a p-value of this, you're saying that 5%, if this was 5.1%, that's too common. But 4.7%, that's rare. Well, I know you got to draw the line somewhere, but all of this is not like set in stone. And you need to take these certain things into consideration when you're setting that alpha level and when you're making your conclusions. If you're implying some dramatic shift or change of opinion or policy, if you are in a position of power, whether that's through a company or government position, something like that, and you're a decision maker, and the ramifications of making one of these decisions based off of this data analysis is very costly, either in a financial sense or a time and energy sense, or maybe all of the above. That's something that you want to think twice about. We talked a lot about the direction of the alternative hypothesis last week. I think this is kind of where we left off on Thursday, where we're talking about the sample size. And we know how the sample size can directly influence your results. It can influence your p-value. And this makes sense, I mean, mathematically and from a practical sense. I've been saying that the bigger the sample size is, the more certain you are that this is truly what's happening in the population as a whole. Okay? But there are some limitations with that. If you get a very, very large sample, all you need is a little difference in the numbers in order to achieve statistical significant results. I think I had mentioned on Thursday that the famous case study with aspirin and reducing the risk of a heart attack in adult males. That was across a sample of 22,000 people. So about half of them took a placebo, about half of them took a daily dose of aspirin, and they followed them for about 4 or 5 years, and they found that the rate of heart attack in the placebo group was about I think it was like 1.9 for every 1,000 people. 1.9 heart attacks for every 1,000 people. And for the aspirin group, it was like 0.7 heart attacks for every 1,000 people. So it's a difference of like less than 1%. And we're not even talking percents here, we're talking per 1,000. But that very small difference was actually more than cutting the risk of a heart attack in half. And it turned out to be a statistically significant result because it was across such a large group of people. And they were certain this is truly making a meaningful impact. Okay? And they had pretty good p-value with that, which gave them practical significance. So the size of the p-value, not just the yes or no answer of it's less than 0.05 or it's not, the size of the p-value goes more towards practical significance. I have an example here. This is directly from the textbook that kind of illustrates the size again. A sample survey shows that significantly fewer students are heavy drinkers at colleges that ban alcohol on campus. Kind of makes sense, right? Now, quote, significantly fewer is not enough information to decide whether there is an important difference in drinking behavior at schools that ban alcohol. How important an effect, or how important it is, depends on the size of the effect as well as its statistical significance. If the number of heavy drinkers is only 1% or less at colleges that ban alcohol than other colleges, this is probably not an important effect, even if it is statistically significant. Okay? Now, we saw that difference of less than 1% across that monstrous sample size. We don't have the exact numbers here, but it's probably not that large. So a difference of 1%, you probably wouldn't describe that as being statistically significant, okay, or being significantly less. It says, in fact, the sample survey found that 38% of students at colleges that ban alcohol are heavy episodic drinkers, compared with 48% at other colleges. Now that difference of 10%, okay, that one's large enough to be important. Now it goes on to say, don't forget about what we talked in the beginning of the year. Of course, this would be an observational study. It doesn't prove that the alcohol ban directly reduces drinking. It may just be that colleges that ban alcohol attract more students who don't want to drink heavily. And that makes sense. The last part right here. Beware of multiple analyses. Now, this can seem a little bit confusing at first, because we're used to thinking of the passionate doctor who says, well, we're going to figure out what's wrong. We're going to run this battery of tests and figure out exactly what the issue is and deal with it. But in a statistical sense, there's really not a reason that you would have to be running multiple tests. Okay? Because think about that design process. Set the hypotheses, collect your data, analyze your data, make conclusions. The two steps that are oftentimes reversed, and you're really not supposed to do this, are collecting the data and then setting the hypotheses. Now, the reasoning of statistical significance, it works well if you decide what effect you are seeking and then design your study to search for it. Okay. What am I looking for? Set the hypotheses, go out, collect the data. You're going to be using a test of significance to weigh the evidence that you collect. Now, what happens is, if you throw a whole bunch of crap against the wall and see what sticks, see what comes back as significant, well, our process is acknowledging that some of the times we're getting things due to chance variation alone. And that's what we have in this example right here. There was a question about 15 years ago, said, might the radiation from cell phones be harmful to users? Many studies have found little or no connection between using cell phones and various illnesses. Here is part of a news story of one of these studies. It had said, a hospital study that compared brain cancer patients and a similar group without brain cancer found no statistically significant association between cell phone use and a group of brain cancers known as gliomas. But when 20 types of glioma were considered separately, an association was found between phone use and one rare form. Puzzlingly, however, this risk appeared to decrease rather than increase with greater mobile phone use. So they found an association, but it was in the opposite direction from what you would think it would be. Kind of like that one example we had before where it had the implication of a negative relationship between smoking and lung cancer. Man, that didn't make any sense. Okay? Same thing here. They found one relationship pop up in one of their 20 tests, but it was in the reverse effect. It found that cell phone use actually reduced the risk of this brain cancer. Now, it says, think for a moment. Suppose that the 20 null hypotheses are all saying there's some form of no association between cell phone use and this cancer. And all 20 of those null hypotheses are true. There is no relationship. But each test has a 5% chance of being significant at the 5% level. That's what that alpha value of 0.05 means. You're saying that 5% of the time you're going to get a result like this due to natural variation alone. So just by chance, when the null hypothesis is true, you're going to get a value this extreme that you would reject the null and accept the alternative. But 5% is 1 out of 20. We had 20 tests, one of them comes back as significant. Okay, that's built into the process, that you're acknowledging that these are imperfect tests, and sometimes you're going to get results just by chance alone, which is important to recognize because there's no red flag that stands out that this is the one that's bad or this is the result that's not actually true. It's part of going through the process and recognizing that you're never completely certain about that, especially if you have a p-value that just barely cuts it over that 0.05. Questions on that? Okay, last thing about designing these tests, and then we'll get into our error analysis, is that you are designing this for your data. Okay? You're creating the hypotheses, then you're collecting your data. You should not go into this with, is 50 people a good sample size, 100 people? You want to have everything planned out. So our equation for margin of error, okay, this is that step that we take, usually 2 above, 2 below our sample mean when we're creating a confidence interval, z star, again, usually 2, times our standard error, sigma over square root of n. It's probably a better thought process to have in mind what we want our margin of error to be and get a sample size that will achieve that. So you can just algebraically solve this equation for n, and it turns into this. That sample size is found by taking our z star, again, usually 2, times the standard deviation divided by the margin of error and square all of that. So we'll keep this in mind as we start to plan out our own study that we're going to be starting in a couple of weeks. Questions here? All right, so our last idea for the day is talking about error. And when we were first introducing the hypotheses, I gave you this analogy of our judicial system, that we have the presumption of innocence. You're innocent until proven guilty. So we could think of the null hypothesis as being that the person accused of this crime is innocent, and that the alternative hypothesis is that the person is not innocent. They actually committed this crime. Now, it's the job of the jury to weigh the evidence that is presented to them and make a decision about the innocence or the guilt of that defendant. Now, what if a mistake is made? Okay. You need to think about the consequences of that. Let's say it's a murder trial. Okay. Now, it's obviously a mistake if the jury comes back and they claim that the suspect is guilty, but later it's found out that no, actually the person is truly innocent. Okay. What are the consequences of that? Well, you have an innocent person sitting in jail for a crime that he or she did not commit. And secondly, the person who actually committed the crime is running free. And if you think you have the guilty party sitting in jail, nobody is out looking for that truly guilty person. And the family of those who were victimized, they think that justice has been served. Okay, so I guess they feel good about that, but I mean, they're still impacted by it, obviously. Well, what's the other type of mistake that the jury could make? We said here that they could find the person guilty when he or she really did not commit the crime. The other thing that could happen would be that they find the person not guilty when they actually did do the crime. And in that case, the consequences are that this guilty person is running free. But at least there's no innocent person sitting in jail for a crime that he or she did not commit. So in that kind of a sense, you can kind of think that this is the more consequential error that could be made. Okay. That's kind of like what we're doing with our hypotheses. This is just kind of illustrating that again. Okay. We cannot rule out the defendant is innocent, so he or she is set free without penalty. Criminal has been erroneously freed. Or we believe enough evidence to conclude the defendant is guilty, an innocent person falsely convicted, and the guilty party remains free. This is usually thought of as being the more serious case. In a medical scenario, we had talked about, I had given a lesson that I can't remember if it was to you guys. I think it was my Tuesday Friday classes right before winter break about the imperfections of the COVID tests, and especially those rapid response tests that a lot of the criticism was about them, that they were only like 55 or 58% accurate in terms of identifying a positive test when the test is truly positive. And it was that whole idea with specificity and I forget the other name for the term. But when we're performing a medical diagnostic test like this, okay, they are imperfect tests on diseases that are hard to track, and diseases or viruses that are hard to track. So you're going to get some false positives and false negatives, and you need to take those into consideration when you're looking at your results. So a false positive, it tells you you have the disease when you don't really have the disease. And a false negative tells you that you do not have the disease when you actually do. So think about the consequences of each of those types of results. Okay? think of it as our null hypothesis, you don't have the disease. Alternative, you do have the disease. Okay? Our first choice, the medical practitioner thinks that you are healthy. The test result is weak enough to be negative for the disease. The potential error of that is that you have the disease, but you're told that you do not. This is a false negative. So the consequences of this, well, you're told, or you have the disease, but you're told that you're not pursuing treatment for this disease. If we're talking about this virus, then you're potentially spreading it to others. Okay? When you think that you are healthy, those are the ramifications of a false negative. Now, the other alternative here is that the medical practitioner thinks you have the disease, but the test result comes back strong enough to be positive. You are healthy, but you're told that you have the disease. This is a false positive. So the ramifications of this, well, in the case of COVID, you're isolating, probably taking some prescription drugs that you don't actually need. Which of these errors is more serious? Well, I mean, it depends case by case, but usually, based off of the disease and the consequences, one stands out as being a little bit more impactful than the other. So taking that into our hypothesis testing process, the two types of error that can be made are just simply referred to as type 1 and type 2 error. Now, let me be clear about something. When we're talking about error, we are not talking about making a mistake along the way, like mathematically or in our data collection process, like all of those flawed things that we could do with our experimental design. That's not what we're referring to. Okay? When we are referring to our error analysis, it is the assumption that all of that data is collected and analyzed in an accurate manner. But an error happens due to that natural variation, where we accept the null because the p-value tells us, or we reject the null because the p-value tells us to, but we shouldn't have. Or we fail to reject the null when we actually should have. Okay? That's what we're referring to here. Now, the way I remember this, and I found that this is helpful for students, because we have definitions here, we have a little chart, but it can be difficult. The number of the error is the hypothesis that is actually true, but your test makes you believe that the other is true. Okay? So think of it like this. We have our null hypothesis, and we have our alternative hypothesis. The null is thought of as hypothesis number 1. The alternative is thought of as hypothesis number 2. So a type 1 error can only be made if the null hypothesis is actually true. But you had a p-value that was less than 0.05, so you rejected the null, and your process told you to accept the alternative. But the null is actually true. That is a type 1 error. A type 2 error can only be made if the alternative hypothesis is actually true. So the alternative, number 2, is actually true, but you got a p-value that was bigger than 0.05, so you failed to reject the null. And you believe that the null is true. We see these results summarized on this table right here. Okay? The decision made. Okay? We ran our test. We found the defendant not guilty, or we found the patient to be healthy, or we failed to reject the null hypothesis. Now, if the person really is innocent, and the person really is healthy, and the null hypothesis really is true, pat yourself on the back. That was the correct thing to do. Well, no, I shouldn't say the correct thing to do. I should say that that was the correct result. But if that person really is guilty, or the person really does have the disease, or the alternative hypothesis really is true, that second hypothesis is true, we thought that the first one was. That is a type 2 error. Or coming down here, if the result of our test, we found the defendant guilty, our test comes back that it's diseased, or we accept the alternative hypothesis, we think that the second one is true. But if really the person's innocent, or the person's healthy, or the null is true, that's a type 1 error. Okay? But if it all works out like that, then we did the correct thing. So what you are doing with this, at the end of your test process, you are acknowledging the possibility of a type 1 or a type 2 error based off of your conclusions. If you reject the null and accept the alternative, you believe the second one is true. If you made a mistake, then the first one would have been true, and that's a type 1 error. And discuss what the consequences of that might be for your test. That person's not getting the medical treatment they need, the guilty party's running free, whatever it might be. Sometimes the consequences aren't really that impactful, but we're trying to plan this out as part of our process. If we have these two errors, and one of them stands out as being much more catastrophic than the other, we want to take that into consideration when setting that alpha level. Right? If it's really catastrophic, if we have a type 1 error, where we reject the null when we really shouldn't have, well, maybe we want to make it real difficult to reject the null. Okay? Play it safe. That's the type of thing that we're considering here. This mean here to kind of underscore what these are. Okay? The null hypothesis in this case would be not pregnant. Alternative would be pregnant. So you go into this under the assumption, it is a medical test, I guess, diagnostic test, that you're not pregnant. Run the test. Doctor comes back and tells the gentleman, sir, congratulations, you're pregnant. And that's a type 1 error. Clearly, the null is true, but they made the wrong decision. Okay? They rejected the null when they should not have. This case, I mean, you never want to assume that a woman is pregnant and ask when she's due or anything like that, but it appears like this woman is, and the doctor is saying, you're not pregnant, okay? You're saying that the null is true when really it should have been rejected, okay? We have the second hypothesis actually true, so you're going to have a type 2 error in that case. Now, like I said here, I kicked my screen around. We can only specify the conditional probability of making a type 1 error given that the null hypothesis is true. Remember what the p-value represents. It is a probability. It's the probability that the null is true, that you expect this to happen, and that your evidence that shows this, that would happen due to chance variation alone. So if it's less than 5%, if we have a p-value of 3%, we are saying that, well, there's only a 3% chance that the null hypothesis is true. That's pretty rare, okay? Less than my qualifier of 5%, I'm going to reject the null and accept the alternative. If you do that and you're wrong, that is a type 1 error. The p-value is the probability of a type 1 error. Okay? That is important to recognize. The p-value is the probability of a type 1 error. Now, a type 2 error, think about what's happening with the type 2 error. In a type 2 error, the alternative is true. But you ran the test and you got a p-value that was not significant. So you got something like 0.09, we'll say, on the 0.05 level. So you're saying that 9% of the time we're going to expect this and get this. That's natural variation. That's not all that uncommon. I'm going to play it safe. I'm going to fail to reject a null. But if that's a type 2 error, then that means that the null or the alternative is actually true. That the evidence is out there. You just didn't have it to be able to mathematically reject the null hypothesis. It's out there. It's hard to say why you didn't get it. A type 2 error is usually a little bit more difficult to process. Because you cannot quantify the probability of a type 2 error. Again, the p-value just represents the probability of a type 1 error. So if you fail to reject the null, there's the possibility of a type 2 error, but you don't know how likely that is. Okay? The probability of doing that depends on which part of the alternative hypothesis is true. So computing the probability of making a type 2 error is not feasible. So you need to kind of weigh these potential consequences of your error when setting your hypotheses and setting that alpha level of significance. Now there's a more complex idea called the power of a test. They do this in AP. Ch18 doesn't require it, so it's not really worth us getting into. But the power of a test is the probability of making the correct decision when the alternative hypothesis is true. And the book does talk about this at the end of chapter 18 if you wanted to look into it. But it's not worth it for us. And if the population value falls close to the value specified in the null hypothesis, then it is difficult to get enough evidence from the sample to conclusively choose the alternative hypothesis. Okay. Essentially what the power is it's the magnitude of that p-value. And I said there's a difference between a p-value of like 0.047 and 0.00001. But that helps us when it's a type 1 error. When to reject the null hypothesis, consider the consequences of the two potential types of errors. The consequences of a type 1 error are very serious, then only reject the null hypothesis if p is very small. Maybe you want to set that alpha level down at like 0.01 or 0.001. But if a type 2 error is more serious, well, you should be willing to reject your null hypothesis with a moderately large p-value. 0.05, 1.1. Okay? This is not always that common. Right? Usually you want the p-value because the null hypothesis is usually the status quo. It's the safe bet. It's what's currently happening. So what you will be doing is acknowledging the possibility of a type 1 or a type 2 error based off of your results, and talking a little bit about what those potential consequences might be. Any questions here? All right, a little bit of long-term planning here. We have a homework assignment for chapter 18 that is going to be due on Thursday morning. Okay? So Thursday morning, I'll see you next on Wednesday, we're going to start to review a little bit for our next quiz, which will be a week from today. All right, so sampling distributions, confidence intervals, and tests of significance. Okay. Wednesday, we'll start our review. Thursday, more completely get into all of that and practice and make sure we're all ready to go for a Monday quiz. Right now, you have some time, good 25 minutes or so, that you can get a good chunk of this homework assignment done, or at least started. I will say there's not much math in this homework assignment, and most of it is just kind of analyzing the process, stuff that we've talked about here. And so hopefully that makes sense to you. If it does not, ask me about it. Any general questions right now? All right, let's use this time to get started.